Bismillah ar-Rahman ar-Rahim. Alright class, Assalamu alaikum and welcome to the first lecture of week 6, where we were trying to derive the expression of electric field intensity for a one-dimensional charge distribution or source distribution, because charge can be the source of magnetic field, it can be the source of electric field, it can be the source of electromagnetic field, but we are interested in electrostatic situation. So the source in this case would mean a charge which is not only constant with respect to time, but is also not moving, or which is actually stationary. So this on the board you can see here that this is where we left our last lecture of week 5, in which we were actually trying to figure out which coordinate system we should use, and we said that in order to decide which coordinate system we should use, there should be some scientific way of doing, but that should not that can be left to your imagination and pure intuition. आप इसको वजदान पे छोड़ सकते हैं, but there should be some scientific way of explaining or deciding which coordinate system we should use. Why is it important to decide the appropriate coordinate system to work in? Because we have seen in a couple of examples that using a correct coordinate system leads to an expression which is very simple and intuitive, meaning that the physical nature of the field can be sensed, if not accurately decided, but it can be sensed through a simple expression using an appropriate coordinate system. Had we used some inappropriate coordinate system, we would definitely get the expression for electric field, but that field will not be intuitive, meaning that that field, seeing at the expression of that field would not give us any idea of the field itself, so that would not be intuitive. So in the case of point charge, we said that if we had one point charge, we should use a spherical coordinate system where we should have the origin on that point charge itself, and if we have more than one charges, then definitely only one can be made the origin. So in that case, we should better use Cartesian coordinate system. If we have a cluster of charges, definitely we should use the rectangular coordinates or Cartesian coordinate system, because there is no symmetry found over there. But let's see, in the case of infinite line charge, infinite uniform line charge density, we said that okay, let's try to let's put the intuition aside and try to figure out scientifically how to decide which coordinate system we should use. And we said that okay, to do that we have to do some symmetry checks. Okay, so there were two clauses of symmetry check. Clause number 1 was that we should look for the coordinate on which the magnitude of the field is expected to change, and we took an infinite uniform line charge which was described by its line charge density, and we did put that line charge on z-axis and tried to figure out that if we work in a Cartesian coordinate system and change x and y and z, and then in that case which coordinates would affect the magnitude of the electric field, or in other words, because we don't know the expression precisely, what we were actually looking at, that changing which coordinate would change our distance with respect to the source itself. So that's the reason why we used the word expected to change. It may turn out later on that a particular coordinate which we were expecting that it would change the magnitude of field, it may turn out later on that it is actually not changing the field itself. But for symmetry check, we try to see the expectation. Definitely, if we are getting closer or getting away of the source, the magnitude of the field intensity is expected to change. So this is what we were looking, and at the end of the symmetry check clause 1, we decided that okay, now we are going to use cylindrical coordinate system, because we have got only one variable which affected the magnitude of the field, and that was rho. The second symmetry check would be done while adopting the cylindrical coordinate system as our base coordinate system for line charge density, and deriving the expression for electric field intensity. Later on, while deriving the expression for electric field intensity in cylindrical coordinate system, we will have to hunt down that which of these three components, that is rho and phi and z, which of these three components are expected to be there at the in the final expression. So this is symmetry check clause number 2, which we will perform while deriving the expression. So let's move on, inshallah. All right, so let's continue, and we were discussing field of the uniform infinite line charge density, and let's say here we have got that infinite line charge, which has got the density rho L. All right, so and we have decided to use cylindrical coordinate system, so that's fine. How about we make this line charge z-axis? Why? Because doing so, because this is an infinite line charge, doing so would allow us to take this line charge as the central axis of the cylinder. Okay, if we had chosen it to be like x-axis, we would not have been able to do that. Okay, or y-axis, we would not have been able to do that. We would not have been able to take x-axis or y-axis as the center of the axis. So when we can use a certain parameter as one of the coordinates, so better do that. It's always advisable. So if we make the z-axis, which is infinite obviously, as the if we make the z-axis on the infinite line charge density, that would give us a very important ability to take any point. If we want to find any field at any point, if we put the line charge on z-axis, and if we want if we have the field point anywhere, then the perpendicular distance of this field point and the line charge or the z-axis would be rho. Okay, so that way we'll be able to use the line charge as the central axis for this cylinder. Anyway, so if this is z-axis, so obviously this is x-axis and this is y-axis. Now this is an infinite line charge on z-axis. We don't have any formula for that for finding the electric field intensity of an infinite number of charges, but what we can do is that we can divide this infinite line charge into increment or differential lengths, with each length having the size of the z, differential z. Why z? Because the line charge has been segmented along the z coordinate. Okay, so if I divide this line charge into infinitely small segments, each with length dz, then each segment can be treated as a point because it's very small. We have talked about the incremental and differential entities, so this is differential. Pardon me if I had used unintentionally the word incremental for this, but this is differential. So if this is differential length, so it can be treated as a point, and the amount of charge enclosed in this differential length would be dq, differential q, and that amount of charge would be, we know that from our previous discussion of charge densities of various dimensions, dq upon dz will be the line charge density. So it means that if I needed the charge which is enclosed in that differential amount of charge which is enclosed in this differential length, what I'll have to do, I'll have to multiply it by dz, multiply the charge density by dz, since we are dealing with uniform infinite line charge. So no matter where I take this segment, that segment will enclose the will contain the same amount of charge dq, and that can be figured out from that formula. Anyway, so now with respect to this point charge, I can find the formula of the field at any point within this three-dimensional space, but for the sake of derivation, we are taking a point on y-axis. Why we are taking that, that will be clear momentarily, but we are taking a specific point on y-axis as a field point. Later on we will try to generalize this result, the result that we'll get by taking this field point on the y-axis. So the field point is on y-axis, so definitely the coordinates would be 0, y, 0, whatever the value of y coordinate is, whatever the distance of this point with respect to origin is, we'll take that as y. So to keep treating this this charge as the point charge, what we have to find to find the field at this point due to this point charge, we'll need the distance between the source point and the field point, meaning the length of this line is what is required. Why? Since we can treat this this segment as a point, and the charge enclosed in that point, on that point as a point charge, we can use the formula for formula of electric field intensity for the case of point charge, which was the charge divided by 4 pi epsilon naught divided by the distance between the field point and the source point cubed multiplied by this. This is nothing but distance between the bracketed term is nothing but the vector which starts from the field from the source point and terminates at the field point, meaning this vector. This is what? This is r minus r prime. This is something which you all are already aware of. Okay, so this is what we need in order to find the contribution of the field at this point due to this differential point charge. So the contribution at that point will be due to the differential point charge will be the differential contribution to the electric field intensity. Okay, we cannot write E here because E would be the intensity at this point due to whole line charge, but we are not talking about that right now because we don't have any formula for that. But what we have the formula for is for the differential contribution of electric field intensity at this point due to this differential line segment, and that is nothing but the charge stored in that differential segment is nothing but dq. Okay, and 4 pi epsilon naught is nothing but constant. So what about this r and r prime? This r is the position vector locating the field point. This r prime is the position vector which is locating the source point. So let's say the height of this segment which we took here as an example, the height with respect to origin, that height is, let's say, z but we, as I said earlier, always associate a prime for every entity which is associated with the source. So that's why I'm using z prime as the height of this segment with respect to z equals to 0 plane or origin in simply. Okay, so this is this height. So the position vector which locates this segment should start from origin and should terminate at this segment. You can treat this segment as a point. So the position vector will be r prime. Okay, r prime. So r prime, the coordinates of this point is nothing but 0, 0, z prime, and coordinates of origin are 0, 0, 0. So you can you know the coordinates of head and the coordinates of tail. So you can simply write the expression for position vector locating that source segment. And now the position vector which locates the field point should start from origin because it is position vector and terminate at this field point, and the coordinates of both the ends are known. So I would directly write it like this. So this is in Cartesian coordinate system, right? But we are working in cylindrical coordinate system, so we should convert this vector r, position vector r, into its equivalent cylindrical coordinate representation, which you guys will do yourself because you know how to do it. I am directly writing the answer after converting the position vector r from rectangular to cylindrical coordinate system. Okay, so there we go. This length is y. Okay, 0 by 0 is this point. So we have got the position vector to locate the field point. So now this numerator, in place of charge we have put the charge dq 4 pi epsilon naught. Now we need r minus r prime, which is nothing but rho a rho minus z prime az, and the magnitude r minus r prime would be rho square plus minus z prime square, or in other words it would be under root rho square plus z prime square. Okay, so now let's replace these values here. So in place of r minus r prime, we can write rho a rho minus z prime az, and in the denominator, in place of the cube of the magnitude, we can write this, which is nothing but rho square plus z prime square raised to 1 upon 2. So what we can write here is rho square plus z prime square 1 upon 2 times 3, meaning we have taken the cube. I hope you're able to see it, and yes, you are able to see it. All right, so in order to find the complete field at this point, due to this whole line charge distribution, what we can do is nothing but we can just take the integration. We can just integrate this expression, but before mindlessly proceeding and integrating this, how about we give a thought to this final expression which we have written on the left hand side of the board. Let's give it a thought, okay, and then we'll try to proceed with the integration. So now what thought we should give it, we should give to this expression is nothing but the symmetry check point number 2, and that forces us to think a little bit symmetrically, that the field due to this point charge, which we have taken z prime units above the z equals 0 plane, let's say the field due to this point charge at this field point is this d differential electric field intensity. Obviously, according to Coulomb's law, you know that the force acts along the line joining the field point and source point, and it is always, you know, repulsive if this is a positive charge, and it will be attractive if it is a negative, if this line charge density would be a negative line charge density. So for the sake of argument, for the sake of this derivation, we are just considering that this rho L is of some positive value. So let me write this this component of electric field intensity, which is due to this differential charge, point charge. Let me call it dE1. Okay, I'm writing it with red marker. I hope you would be able to see it like this, but color does not matter. All right, so if I take a similar size of differential length, this time below z equals 0 plane, how much below? Z prime units below. Let's say I just take it the differential length over here, and that differential length has got the value dz. Because this differential length is on the source, we always add a prime to it, and I should also write prime here, and I should also write prime here, because this is, you can just treat it as dz. बस just क्योंकि हम सिर्फ हर सोर्स क्वांटिटी के साथ प्राइम लगाने की कोशिश करते हैं, इसलिए हमने इसको dz प्राइम लिख दिया, otherwise this is nothing but dz. All right, so no, the point charge enclosed in this differential length would be dq, and since this is a uniform infinite line charge, uniform line charge density, so the amount of charge enclosed in this differential length will be the same as was in this case. Now, since this distance is again z prime, earlier it was z prime units above the z equals 0 plane, this time we are taking a differential length z prime units below the z equals 0 plane or the origin. What will happen? If we want to find out the field, differential amount of field at this field point due to this differential charge, what we would need the length joining the field point and the source point, okay, and a vector in this direction, just as we did here. Okay, but we are not going to repeat that here again. We are just trying to discuss the second clause of symmetry check, which by the way states that, just for your reminder, stated that we should look for the components of electric field intensity which would be there at the end of the derivation. You know that we have already chosen to work in cylindrical coordinate system, so we should expect a field which must have a rho component, which may have a phi component and a z component. So symmetry check clause 2, we are trying to figure out at the end how many of the components would be present, and if there is any component which we can figure out earlier before reaching at the end of the derivation. If we can figure out any component which may not be present, why not cancel that component before integrating this final expression. This expression is telling us that if we would integrate this, so we can have a rho component, we should expect a z component. All right, so before doing the integration, let's try to check the symmetry once again. for the possible elimination of any of the two components. So that's what we are doing here right now. That we took earlier this patch, this differential length, which enclosed a differential amount of charge, and now we are taking a symmetrical source component just below the field point, just below the z equals 0 plane, in order to assess whether there is any symmetry which would assist us in eliminating any of the component. All right, so this expression tells us that, all right, we should not expect any phi component, but let's see whether we should expect any rho component or any z component. Let's see that. So this point charge will apply, okay, since this distance is the same as this one and this distance is the same as the previous one, so this distance will also be same as this distance. So, and the amount of charge is also the same, so the distance between the field point and source point is same, the amount of charge is same. So what we should expect is differential contribution of electric field intensity due to this point charge in this direction of this green arrow. Okay, I hope you would see it in green. The length of the arrow, this green arrow, would be the same as the length of the arrow of this red one, this red arrow. Okay, but both would have different orientation. Nevertheless, the angle which this green arrow makes with respect to y-axis would be the same as this red arrow makes with respect to the x-axis. So if I resolve, with respect to the y-axis. So if I resolve this green arrow into its rectangular component, I will get a vertical component and a horizontal component. Similarly, if I resolve this red arrow into its rectangular component, I'll get a vertical component and a horizontal component. All right, so the horizontal component will add up while the vertical components will cancel each other. So vertical component is which component? This is obviously the z component. So by checking the symmetry, we know that, okay, this the length of the line charge above this line, above this point, is infinity, and the length of the line charge below this point is infinity. So this point, the field point, has got infinitely long charge above it and infinitely long line charge below it. So there would be at every place above z equals 0 plane, there will be a point charge which will cancel its symmetrical that will, what should I say? I should say that there, for every point above z equals 0 plane, there will be a corresponding point below z equals 0 plane which will cancel out the vertical components. All right, so at the end of the expression, you would not have any z component associated. You will only have the rho component of the field. So before attempting mindlessly, attempting the integration of this complex expression, let's do the symmetry check. And after doing symmetry check, we realize that after doing the integration, the overall field will not have the z component, because of the reason I just explained, that there is always a point below the z equals 0 plane for its corresponding point above z equals 0 plane, which will symmetrically cancel out the z component as I just showed. So at the end, we can write that before attempting to integrate this, we should realize that the z component will finally be 0. So why even add it? Why even keep it in this first expression, in this expression at the first place? Why keep it when at the end of the day it will be it will be evaluated to be, it will come out to be 0. So we have just removed this z component out of this expression. We have thrown it out. All right, and now instead of dq, okay, instead of dq we can write rho l dz prime. Okay, and instead of this I'm just rearranging it, rho l rho dz prime. Okay, so the variable, now we can integrate it. All right, so let's integrate it. If we integrate this expression, what we'll get the complete electric field intensity at this point, field point, due to this whole line charge. All right, so let's try to integrate it. So this integration would be double, triple, or single? Definitely it will be single. Why? Because there is only one variable of integration. Which variable of integration is this? With respect to which variable would we integrate this expression? Your answer should be with respect to z, क्योंकि हमने लाइन चार्ज को डिसइंटीग्रेट जिस वेरिएबल की रेस्पेक्ट से किया था, उसी वेरिएबल के रेस्पेक्ट से हमें उसको इंटीग्रेट करना पड़ेगा. The variable with which we disintegrated the line charge or the source was the z variable z. So we should integrate the variable. We should integrate this expression with respect to the same variable with respect to which we disintegrated the whole line charge. So for the integration, everything which is other than z can be treated as constant and thrown out of the integral sign. So I am doing it right now. So rho l is a constant line charge density, rho is a constant because we are integrating with respect to dz, and this unit vector a rho is constant divided by 4 pi epsilon naught. All right, and the rest of the expression is going to be integrated, which is dz prime divided by rho square plus z prime square, and the integration as z goes from minus infinity up to infinity. So this is what we are going to get. Now doing the integration and substitute integration by substitution method, and that substitution will be z prime is equals to rho 10 alpha. Okay, now I use this substitution to find the expression, final expression. I'm not going to give the details here, you can do it. I have just given you the substitution. Use this substitution and integrate it, put the limits, and you will end up in the final expression, which would be this. So this is the formula for finding electric field intensity, vector electric field intensity due to an infinite line charge, infinite uniform line charge density. All right, where this rho l is the density of the line charge, 2 pi epsilon naught is constant, epsilon naught is permittivity of free space. This rho is what? This rho is nothing but rho is what? If this is the field point, you want to find the rho, just drop perpendicular. Rho kya hai? Rho is nothing but radius of the cylinder. That was the reason why we took the infinite line charge on z-axis, so that line charge would become the central axis of the cylinder. So this is rho, nothing but rho. Okay, the perpendicular distance between the source point, between the field point and the line charge is rho. Okay, and what is this arrow? Arrow is nothing but the if I want to find arrow at this point, in which direction should I move? I should move in a direction in which not the value of z, neither the values of z nor the values of phi should change. Only the values of rho should increase it means that I should move in this direction. This is the direction of arrow. Is it? Is it? I hope I made myself clear. So this is the direction of, this is arrow, primitive unit vector. So now, although we have derived the expression for a field of uniform infinite line charge density in a particular scenario, that we did put the infinite line charge on z-axis and we took the field point on y-axis. But this expression tells us that if we just understand this expression, we can find out the field of an infinite uniform line charge in any scenario. We only have to recognize the mechanics of this formula, and the mechanics is simple. Just at the numerator put the charge density divided by 2 pi epsilon naught, this is constant, and by the distance between the perpendicular distance between the field point and the line charge. This is nothing but perpendicular distance between the field point and line charge. And arrow is what? Arrow is nothing but the direction along this perpendicular, along this row, along this perpendicular, and it is away of the source. It will be point away of the source if this line charge is positive, and it will point towards the source if this line charge is negative. As simple as that. Because in practical life, you may have more than one infinite line charge density. In case of, for example, twisted pair cable, in case of, for example, transmission lines, power transmission lines, you have more than one infinite line charge, flowing from one side to another side. In that case, okay, if you take one line charge as the z-axis, what about the second one? How would you do that? So in that case, or in general, let's say this is xyz, and we have an infinite line charge, parallel to z-axis, not on z-axis, parallel to z-axis. And let's say this, we want the point, we want to find the field at point, let's say 1, 2, 3, somewhere here. Okay, 3. This is the field point 1, 2, 3. And let's say this line charge density is positive. Infinite line charge density is positive. Okay, so how we can find it? Now this line charge is not on z equals 0 plane. Now mind, if we want to find it, we will just keep the value of this, let's say it is 2 microcoulombs per meter. Just put 2 microcoulombs per meter divided by what? 2 pi, okay, epsilon naught. Now you need rho. What is rho? Rho is the perpendicular distance between field point and this line charge. Okay, let's say this line charge is intersecting xy plane somewhere on 3, 5. So if it is intersecting xy plane at 3 and 5 and 0, so the perpendicular distance would be, you just drop it here, a point on z equals 0 plane. Okay, so the coordinates of this point will be 1, 2, 0. So now you need this distance only, which can be found out using distance formula. And if this is, as for example, this is a positive line charge density, so this distance will be rho. You just find that out using the distance formula. And then for this arrow, just replace a vector, because you know this point and this point, so you can find a vector between these 2 points which is pointing away of the source. Why away? Because this is positive line charge density. Had it been a negative line charge density, अगर ये -2 for example ऐसी कोई होती line charge density, what you would do? You would simply find a unit vector in the opposite direction. This would be arrow, and this would be arrow when we have got a positive line charge density. Okay, so arrow will be found using these 2 points. Okay, so that's how we work. And similarly, this line charge could be on x-axis, or it could be parallel to x-axis or parallel to y-axis. You should always remember that in numerator you have to put the value of that line charge density. In denominator you have to put 2 pi epsilon naught, and instead of rho you have to find the perpendicular distance between the field point and that line charge density. And arrow is nothing but a unit vector which is joining that perpendicular and pointing in the direction away of the source if the line charge density is positive, and towards the source if the line charge density is negative. So this is how you work in to find the field of an infinite uniform line charge density. So that's it for today. Inshallah, we'll see you in the second lecture, where we'll discuss the field of an infinite uniform sheet of charges. Till then, assalamu alaikum.